All right, so let's try to learn something interesting. Do a thought experiment with me. Let's say that I have a clean, pristine field or region that is completely without any kinds of electric fields. And then suddenly, out of nowhere, boom, we just have one that shows up. And this can be a change. Either we can say it's magic, or maybe I took an electron and I kicked it. Maybe I just did something to cause the electric fields in a region to change. So we see some kind of a sudden increase in the electric field that points up. Based on that, what are some kind of thought experiments we can do based on stuff that we know? Well, really, electric fields are kind of related to a current, right? So a field would cause things to, you know, rotate around them according to Ampere's law. So let's draw an imaginary loop and say along that loop, here I've got some kind of a current, which is related to this sudden E. So by the right-hand rule, I get some circulation around it in the magnetic field that looks like that. And to simplify this loop, why don't we just say, on this side it points into the page, and on this side it points out. So if this is something that's true, that's fine. However, if we draw another imaginary loop, and let's call this one maybe a Faraday loop, we have a sudden magnetic field that points in. This loop doesn't like that because that's a sudden increase in inward-facing flux. So the loop would naturally have to try to push it out. So maybe we'll call that B induced. If it does that, that means it also tries to generate some kind of an EMF around it. And the EMF is really the electric field integrated over the circulation, right? We know E times D is V, so the voltage is really, in some ways, an EMF. And what way would it go? It would follow this induced field for B, and it looks like it goes this way. And this is getting to be a little bit complicated. I wish that I could cancel things out, with an eraser, but I'm kind of stuck. So these two fields would kill each other off because they're equal and opposite. And these two fields would kill each other off. And now I'm left with an E. And we can kind of see where this goes. Oh, well, if there's an E here, then that would produce a field here and a field here. This is the one really that cancels. And then if that's true, then that produces a field here, and that cancels. And you can identify kind of a pattern, right? So this is kind of a daisy chain where Lenz's law and Ampere's law kind of go in lockstep and then help to propel whatever this original disturbance was. It moves away at some speed. We could see a similar thing would happen on the other side, right? So here's this field, which would generate, I guess, let's see, we want to push it out, so it'd be that, which would then produce that, which then produces that, and so on and so on. So it's on both sides. This original disturbance pushes out this way, and technically it pushes out in all directions in a plane defined by that original disturbance. Well, maybe we should ask some questions about how fast does this happen, where I go from Faraday's law to Ampere's law to Faraday's to Ampere's and so on and so on. How quickly can I go from one field to the next and do this handoff over and over and over again through lockstep? I guess these things are related in some way by how easy space can pick up and hold this electric field. So that's the permittivity, and then how easy space can pick up and hold this magnetic field, which is the permeability. And when we do these things together, you get weird units. I don't remember the number, but we get weird units in the end of like seconds squared per meter squared. But I can flip that if I do this. And those units are meters squared per second squared, which is weird, but I can do this. And in the end, this number comes out to be 3 times 10 to the 8 meters per second. This is the speed of light. So light's really an electromagnetic wave. It's generated by some kind of a disturbance in either electric or magnetic flux. And then space doesn't like that change in the flux, whether it's electric or magnetic, and it does something in response. And we know that it's either Faraday's law to turn B's into electric fields, And if you skip ahead a little bit, Maxwell's law will talk about how changing electric fluxes produce magnetic fields. So these things come together and do that. This little comic strip is very low level and kind of a little bit cumbersome, but you should go onto Canvas and check out the mechanical universe. There is an animation that shows this kind of in real time with pretty hilariously dated graphics. I think the original one was from the either late 80s or early 90s with computers at the time. So it's funny and the soundtrack is funny, but it's really a pretty good video that really shows this off. I, in fact, never really fully understood how electromagnetic waves works until I saw this video, and then it's like, it made perfect sense. So you should definitely go check this out, and the link will be in Canvas in the modules. Okay, so what can we do with that? We noticed that the electromagnetic wave had some kind of an orientation, and the electric and the magnetic parts of the wave tend to be together. They're always 90 degrees apart, and we can use the right-hand rule to determine what's the direction of propagation, or what way is the wave moving. To do that, take E cross B, and that will give you the direction of V. And this isn't an equal sign, right? The pointing vector, which is given by E cross B, has some other constants in it, and I think it talks about like the energy density or the energy flux that's transported. I don't care so much about that as much as just what's the direction of E and B based on the speed and vice versa. So if we take our E and point it upwards, and we cross into B, which for us is out of the page, the velocity vector points over here to the right. So this orientation is interesting, and that might springboard us into dealing with Malice's law. When we use a polarizer, it's some kind of device that's designed to take advantage of that orientation. So let's say that we have an incoming wave that, let's say, is vertically polarized, and that's just its orientation, right? The direction that the wave is oscillating, either the E's or the B's. And I want to send it through a polarizer. And this can be something with a polarization axis. And let's say this is our polarization axis at some angle that we call the polarization angle. We want to say how much of the light can get through this. And we can treat this like a screen, right? Think about it like slits where the wave has to pass through. This component that's perpendicular gets blocked by the screen. But this component that's horizontal goes right through it, or parallel goes right through it. So when we do this, if this is our original electric field vector, how much of it gets through? This can be a simple question of E parallel. And what is E parallel? It's E original times some component that's related to this, right? So if that's the right angle, this is the angle that matters. I guess it's the cosine of that angle, because this side is adjacent. So this would be the amount of electric field strength that would successfully get through the polarizer. However, when you looked at Malice's law, we talk about intensities. So I naught is equal to, not I naught, this is, let's say I parallel is equal to I naught cosine squared of this angle. And students often ask, well, why the squared? Because we can see this pretty clearly. Think about something in terms of what comes into our eye. So if this is our eye watching, let's say I have an electric field vector that points up. It goes into the eye, it interacts with an electron, maybe it kicks it out of an atom or does something to deposit its energy, and then we would interpret that as bright because it delivered a signal. If the electric field was nowhere, let's call this bright. If the electric field was nowhere at all, it wouldn't do anything. So that would look dark. And what about in this case, where the electric field is pointed down? What would we call that? Like Would we call that anti-bright because of the minus sign? Right? If there's any one rule on the internet, it's that once you see something, you can't unsee it. I can't have some kind of an anti-electromagnetic wave reach into my eye and pull those images out, right? So that's nonsense. So what's a quick and dirty way for us to get rid of sign dependencies? Just square it. The intensity is related somehow to the electric field squared. I don't know what the coefficients are here, and that should inform you as to how important they are, right? I never use them. Okay, and in Malice Law, we always talk about ratios, right? How much of the original light gets through? Well, that's a comparison of I1 to I0, and if they've all got the same constants, they pretty much just cancel out. So that's why we get squared cosine here, right? We'll have E0 squared cosine squared, and E0 plus some constants equals E squared plus some constants. Doing Malice Law is fairly simple. These should be easy points for everyone to get. I can think of only, off the top of my head, 2 mistakes that a student might make. So if you have kind of proofed yourself against those, you should be fine. Let's talk about the first one. If I have an electric field, and let's say my intensity starts out with this polarization, and I want to send it through polarizer 1, and let's put it in an angle, let's say theta is, I don't know, 30 degrees. And then we'll put it through a second polarizer later, and let's make its angle 90 degrees. And our question is, find I2. What's the final intensity that comes out? Just do Malice Law, right? So if I1 is equal to I0 cosine squared of this angle, we would just put in the angle. And I'm not really good with these, and I don't have a calculator, so let's see, this is a 30 degrees, that's I think 1, 2, square root of 3. And the 30 is over here, so the cosine is the square root of 3 squared over 2 squared. I think, and you have to check this yourself, I1 is equal to I0 3/4, because the cosine is, of course, square root of 3 over 2. Okay, to get to I2, well, that equals, I guess, what we sent in times the cosine squared of the angle, right? And then this would be all the stuff for I1, which will save it, and then cosine squared of 90 equals 0. Is this correct? No. We don't care what the final angle is. What matters is the angle between the polarizer and the light that came directly into it. This light, remember, got bent when it went through this polarizer, so the incoming light is already at an angle of 30 degrees. So this incoming light is already here. This angle was measured relative to the vertical, not relative to the light that came in. So what is technically the actual angle that we want to use here? It's not 90 degrees, it's 90 degrees minus 30, or it's 60. So that means I2 is I1 cosine squared of 60, which is I1 times the cosine of 60. This is the 60, so 1 over 2. Okay, so that's I1 times 1/4. And we know I1, right? All of these things just nest together. I0 3/4 times 1/4 equals 3/16 of I0. And that's what's transmitted through the system. Don't make this kind of mistake where you look at the original and the final and then that's it. You have to look at every individual polarizer in the chain. And if I gave you one of these with 17, you could do it, right? You just have to do them all in order. Do I1, I2, I3, I4, da, 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 all the way out to IN for the last one in the sequence. I think there's some Canvas problems that are online that have like rotating from 0 to 90 degrees through one polarizer, through 2, through like 4, through 10. And I think I have one that has like 180 individual, or 181 polarizers, and say rotate everything half a degree at a time and just see what comes out. And it's easy enough to do, especially if the angles are all the same. Try that on your own and see if you can get through it. So this is one mistake. Don't do it. Always look at each individual polarizer and not beginning and end, because you might be surprised. Okay, so there's another place in Malice Law where we get to cheat, and that's if we have initially unpolarized light. Unpolarized you would call, or you would denote like this with vectors in both directions. And technically a single ray of light can only have one polarization, but if you have a light source like the sun, you have a lot of light rays coming out all at once, and they can have random orientations. So when we talk about unpolarized light, we're talking about one that on average has no preferred orientation. You've got equal probability of all of them as you go around. In that case, if you're unpolarized, I1 through any polarizer is immediately 1/2 of the original that we got. We could do that the hard way and say, well, let's integrate and find the average of all possible orientations as you go through 360 degrees, and then get the statistical average, I guess, of what comes through a polarizer with a well-defined angle. Or maybe let's look at it this way. If this is our light that's got equal parts vertical and equal parts horizontal, and I send it through this polarizer, what comes out? Only that. So how much of the original is that? 50%. You lost half of all your components. So maybe this is a hand-wavy way to kind of brush that aside and say, this is why the unpolarized case is a special case. So that's mistake number 2 you might make. If we did the same problem we did over here, but let's do it now with polarized light or unpolarized light. That'll be your 30. I guess this will be our 90. How does it change? I1 is just immediately 1/2 of I0. And I2 is still I1 cosine squared of 60. And that's because the light is now no longer unpolarized, right? It did take some polarization after the first polarizer. So you get to cheat once. If you have an unpolarized light, the first polarizer, hey, just round off and do the unpolarized assumption. After that, you do Malice Law as usual for the rest of the problem. So in this case, I guess it's I0, or no, it's I2 is 1/2 I0. That'll be I1 times the cosine squared of 60, which I think we said was 1/4. I get a lot more light in that case than I did before. All right, yeah, I don't think there's a lot more about Malice Law, actually. It's really simple, straightforward stuff. You see polarization in a lot of cases, and I will save most of those for the lab demo because we went out to show a lot of them. And maybe we'll do kind of an after action to talk about where you might see polarization and kind of how do we use it in technology.